Did you send me the email?
No, I just got tapped to help make sure this ran with the Zoom and everything.
Okay, but, or you can, or we can just put it, should I try to open my Zoom?
Yeah, I would open the Zoom.
So I'm just
Join the
emailing you.
Zoom, join the meeting, sign in, which?
Well, hang on, no, I just,
Which one?
Lev, I just emailed you the number, so you'll have the link if you look in your Gmail.
Yeah.
Zoom the Zoom camera onto this, or?
It has a.
Mute. Start video. Yeah. So this is another video. Yes.
So the problem is if he talks through his Zoom, and then the room is unmuted, it'll do the feedback. So one of them's after, yeah, the room is, I've muted the room, just so his audio will be good.
Yeah, I've done this before. The speakers in the room can cause it to be cut out before talking, or making noise, so it's better to mute the room.
Yeah. Do you have any, when you're sharing, do you have any sound that you're going to be playing? I think you do, right?
Yeah, I do.
Let's make sure to checkbox this guy.
And also in some moments I want to go to, but this is generous. It's supposed to work.
Yeah, that's like your whole screen or whatever you have on your screen. The blue share button. There you go. Okay.
No, just something is. Oh, this is my screen now.
We have a couple different shots. We have this one in there. Back. Let me join it and see how your audio is.
So, do you hear me? No, maybe
I just need to join the meeting.
no, maybe I should check the microphone.
Yeah,
It's not clear. What?
Oh, I'm just going to join. Just to make sure.
I'm not sure that the microphone is the right one. Should I choose? Which one? Look one. Microphone.
So it should be. I think it's this one. USB and P.
Maybe you can do it.
So it should be microphone, USB.
1, 2, 3. 1, 2, 3. What? Maybe light. This light can be turned off. Christian, do you know what closes this light? This is. One, two, three. 1, 2, 3. Do you hear me here? Well, this will be my first talk in a mask in Tel Aviv. They allow speakers to lectures to be without mask. So I do have experience of giving hybrid lectures, but not without a mask. Let's see if I will survive.
You want to start now?
What?
You want to start now?
Let's see if I want to close at least this light because I think it will be difficult for people to see.
Or let me introduce this one. And
Yeah, great.
Is that the one you want to?
Yes.
okay. So I'll just, is that your microphone? I could just speak like, oh, no, okay. Even better. Can you hear me? No. All right. Hey, everybody. Welcome to this fascinating talk by Professor Lev Vaidman, who's a professor at Tel Aviv University in the physics department. Lev is one of the small band of brothers who did his PhD with Yakir, but he's like me, I did my PhD. Lev has always been our big brother because you're the oldest one, I think, or one of the oldest that's still active with Yakir Aharonov, who he did his PhD with. So basically, I think you're the oldest, Lev. So basically, everything that's happened within the Aharonov cap, I think Lev has had several toes or fingers in. He grew up in St. Petersburg, Russia, and then moved to Israel when you were 18, right? Before then, he won like the top prize. Even as a kid, he won the top prize in the physics Olympiad, right? First place in Soviet Union for all high schools. And then he famously started working with Yakir, and there's all kinds of new fundamental effects with his name on it. One of them, New Scientist magazine selected as one of the top 7 quantum wonders of the entire world. And that's the Elitzer-Vaidman effect. And he's also one of the founders of quantum teleportation, like, beaming up Scotty kind of thing. And he will do an actual demonstration of beaming up during this lecture, right? Right? No? Okay, so maybe he'll cover that, maybe not. So please give a warm welcome for Lev Vaidman.
Thank you for introduction.
Minimize the window on your screen so that it's not blocking.
Yeah, you're welcome to take control of. First, I think the priority for people who are here, and in these days, there are not too many live lectures. In this live lecture, you can ask me. So I think it's important. We'll talk about all kinds of miracles. And in fact, there will be 3 miracles. There will be many words, and will be resolution of these 3 miracles using many words. And of course, there is, yes. So in fact, 2 of them are already mentioned. One is Elitzer-Vaidman bomb tester, another in teleportation, and number 2 is also pretty very famous. If people are familiar with quantum, there is all these Bell inequalities, Einstein-Podolsky-Rosen paradox, and so all these things are kind of connected. For me, they're important because I really believe in something which sounds like science fiction. I believe that there is this world, but maybe, but not maybe. I'm sure that there are parallel worlds. I hope there is one world without pandemic, and then this whole is a pretty big one. And now this is speculation. This I don't know, but about some worlds I really can know. And during the talk, we will make a real experiment. We will split the world. If you perform quantum experiment, I firmly believe that the world split. And there is a link, and if Wi-Fi internet connection will not die, then there is a link to a laboratory in Tel Aviv, which allows us to split the world. But before going what many world is, and before doing this experiment, I want to explain these 3 reasons why I believe that many worlds is the right story. It's not that I like many worlds. I read all kinds of books by philosophers, David Lewis, others who kind of promote idea of many worlds, and was not convinced. I don't like many worlds. I would like one word. But I also want that feel that I understand nature. And I study and teach some of the courses in physics. And the only way for me to believe that we understand today at large, by and large, nature, is that there are parallel worlds. Other things doesn't look reasonable. And the reasons are this, all kinds of paradoxes.
Well, can you tell us what many worlds is?
Later.
Oh, okay. Fair enough.
Later. Okay, so I will start. I will make 3 times miracles. First, I will introduce them, explain them in details, explain many words, and make a resolution within many words. First, I introduce them. Miracle number 1 is this Vaidman bomb tester. Long time ago, Avi Litzur came to me and asked a question. Let's assume we have an object like this, which explodes when you touch it. And the explosion is the only way it interacts with everything around. It doesn't know gravity, whatever, assume. There are all kinds of. The only thing it's interacts with environment is by explosion. So, and can we find it without exploding it? This is clearly paradox, because by definition, the only way to make it interact is to touch it. When you touch it, it explodes. But we found a solution. Quantum mechanics allows to do this. And for me, it's a miracle. If I believe in one word, it's a miracle, which I cannot believe that this can happen. But it does happen. In fact, there were experiments, interaction-free measurements were performed. It works. So if it works and I want to resolve paradox, I will have to believe in many words. Miracle number 2. Let's say we are playing a game. There are 2 persons in different rooms, far away. And to win the game, they have to answer some questions and fulfill some conditions. I will give an example. The questions are very simple. There are only 2 kinds of questions, question X or question Y. Answers might be also very simple, 1 or -1. To win, they have to fulfill this table. If both are asked X, the product should be -1. But if none of if in every other case, XY or YY or YX, it should be +1. And now they're allowed to make strategies. They're sitting together, they prepare, then they take into other rooms. They don't know which questions they will be asked. And they want to be sure to win always. So they try to arrange some strategy. A decided I will say +1. Then B said, oh, I have to say X -1 because to fulfill this equation. If X's are fixed, so then YB is fixed because there's another equation, XA, YB should be +1. So it should be plus. Now we know that XB is fixed, so YA is fixed, should be minus to make the third equation. But if we'll take these 3 equations together, then Y is fixed, YA is fixed, and YB is fixed, and fixed in the wrong way. So no way. You can try and play again something else, but there is a simple way to see that you will never succeed to make a strategy, because to fulfill all these equations, they all have to be correct together. Look on the product. This kind of algebra, I think it's simple. On the right side, we have 1, 1, 1 times -1. It's -1. On the left side, we have XA shows twice, and every other X and Y shows twice. So we have only squares. No way to fulfill this equation. So if somebody will tell you, can you arrange the situation, people in different rooms, they don't know what they will be asked, and they have to win this game. You'll say it's impossible. In fact, you'll be right. This type of game, even quantum mechanics, I don't think it allows, but very similar game, which I will discuss later, can be done quantum mechanically, and classically, it cannot be done. The third miracle is teleportation. Star Trek is kind of great thing, but you know, science fiction. today, teleportation is kind of the key protocol of quantum information, which there is a big revolution. There's teleportation to satellites. The Chinese started it and make all world putting milliards of dollars in all this industry. Quantum teleportation is possible. And we'll see what's paradoxical about it. So, but to see, first I will tell you what I believe it's miracle, or what it's strange. Miracle is a phenomenon which does not have a good explanation. This is a miracle. And if we go to history, even before, more than 2,000 years ago, nothing occurs at random, but everything for a reason and by necessity. There should be no miracles. And about 200 years ago, many physicists believed that the good theory is something like Laplacian universe. And Laplace said that if we will know position on every molecule, every atom, every velocity, then this will allow us in principle to calculate everything, the whole future and the whole past. So determinism is kind of a good idea. Today, determinism is a bad word, and it's happened because of quantum mechanics. And I think it's a mistake. This is really what I want to tell you in this talk. We should not give up about determinism. Even today, philosophers, this is probably the leading philosophers working on these issues, he said that only after long and repeated failure may we entertain the hypothesis that the failure to find deterministic laws does not represent a lack of imagination or diligence on our part, but reflects the fact that nature is not deterministic. After this, he said, quantum mechanics is such that we have to believe in non-determinism. I will say that he will accept parallel worlds, we don't. So one thing for good explanation is deterministic explanation. If science will tell that this we know only with some probability, kind of giving up, saying that the science is limited. It cannot tell what will happen. There is another thing which I think is very important. To give this lecture, I have to come here. I believe that everything is local. Okay, today, of course, I could give this lecture by Zoom from Tel Aviv. But also, this is clearly, it's not immediate. It will be some time until the signal from Tel Aviv will come here. My immediate interaction, it's only local. So this kind of local action, sensible. This I understand. Now, the first, Newton, in fact, was the first to introduce non-local action. I don't know how many, I hope you know about the law of gravity of Newton. Law of gravity of Newton tells me that really, by gravitation, I exert force on moon. Very little, my mass is small, but I exert force on moon. This is the equation. And if I move here, now I exert force in somewhat different direction. And this, by Newton, happened immediately. He invented this, but he himself said that it's crazy. It's inconceivable. No one can believe in it. So he had this gravity law, but he said it cannot be true. He is in a good company. Principle of local action by Einstein. If A and B are spatially distant things, then an external influence on A has no immediate effect on B. And I believe Einstein believed it until his death. This is why he was not so happy about quantum mechanics. Unfortunately, the many world theory came after the death of Einstein, and we cannot know how he would react on this solution. So this is the only good explanation from my point of view. Local one. I have to touch it. I cannot kind of influence it immediately by kind of thinking about this or doing something else. So about Newton, this is resolved. there is a good explanation of gravity. Earth creates field and create not immediately. The field changes with the speed of light. When I move here, the field, my gravitational field will change about what is this, a second later. The gravitational waves go with the same speed as light wave. And when the field is there, this field affects objects locally. And we have this acceleration, local force divided by mass, and we'll get this apple which falls and bring Newton to his gravitational law. But he never knew about the idea of field. So field resolves this. I have no reason because of gravity to believe that the world is non-local. There is a local action through fields. Okay. After advertising the three miracles, I want to go in more details and to say how every miracle works and what is paradoxical about it. So how works this quantum Elitsur-Vaidman bomb test? There is this device which called Mach-Zehnder interferometer. In fact, it's 200 years, even more. This device, people knew about classical light, about waves. If you build kind of a beam splitter piece of glass here and two mirrors and another piece of glass here, and you tune it properly, no light will come here. There will be destructive interference towards here, and all light will go one way. About 40 years ago, Aspect and Grandier performed this experiment with single photons. People also do this experiment with neutrons. We send a single particle, and in principle, if you send it to a beam splitter, it's going another way. In this case, so it can go here or here. But somehow, when in this interferometer, it will it never come here. Because we know from here it can come here, from here it can come here. But if there are two together, there is destructive interference, even for single particles. This is what quantum mechanics tell us, that particles are waves, and they can interfere destructively or constructively here. So Elitsur-Vaidman bomb tester is just this device with single particles. That's just to be to see how it works. You see, it's always come here because there is interference. Waves come here, and here the waves are kind of opposite, different signs. So they did, and here is this together, so it's constructive interference. So to find a bomb, we take this tuned interferometer and place it in such a way that one of its arms go through the place where we suspect that might be a bomb. If there is no bomb, this one cannot click because it's built like this. Interferometer always go here if it's properly tuned and if it's free. However, if we put a bomb there, the interference is destroyed because there will be no wave from here. The particle cannot go through the bomb. So here the particle can go only from here, and there is a chance that it will click here. So if we send, there is sometimes an explosion. But it might also happen, we cannot send one particle, can find one particle in two places. Sometimes explosion, sometimes no explosion. No explosion, the whole wave remain here, and it's continue. And in the end, it has a chance, again, 50 chance of this, so it's 1/4 chance to get a click here. When we get this click, then we get this miracle. We know that the bomb is there. How we know? Without the bomb, this click is impossible. So the fact that the click was there, we know that the bomb is there. We also know that nothing was there near the bomb, because if you touch the bomb will explode. So nothing touched the bomb, and we found the bomb. Impossible game. Okay, this one, as I said, I don't know how to do, but this one I do know how to do. essentially is the same game with 3 people. Greenberger, Hall, Zeilinger. And in fact, if I want to be to give a right credit, I was in a conference where they presented this work and kind of didn't catch the beauty of the idea. They had it for 4 particles, and Mermin came and made it for 3 particles, and I came and made it into a game. And this is a game. This is a game which I told you. There are 3 people. They ask question X or Y, and they should answer 1 or -1, and they should fulfill this table. And again, if we try to make it, let's say plus, they should be -1. X's we know, so this all X's we know. Let's try to fulfill this plus. It should be another plus. Now this we know. With, only what's left is YA. To fulfill the 3rd equation, it should be plus. But then the 4th equation doesn't work. And now you know the proof why I cannot arrange it if I'll try, never mind how. What is the proof? How to prove that it's what? Yes. Multiply all together again. On the right hand side, -1. On the left hand side, you see XA appear twice in the first one and the second one. And every other appear twice. So we have to fulfill all these equations, and the product also have to be fulfilled, but the product cannot be fulfilled. So cannot be done. Now, we have a quantum mechanics. I will not give you the equation, although they're not so complicated. They tell that if you start with 3 spin half particles, it may be 3 photons with polarization. In this particular state, which is called GHZ, or maybe should be called GHZ Mermin, then what you'll do, everyone gets 1 of these particles far away in different rooms. Then somebody came and asked question X or Y. If they are X, then you ask about polarization of a spin. There is a magnet you put in particular direction and ask if it go up or down. So you ask question X, you put it in X direction. You ask Y, you put it in Y direction. Everyone do this, both A, B, and C. Y measure in X, if you ask X, measure X direction, Y, measure Y direction, in all of them. Now, the rules of quantum mechanics tell us that it must be fulfilled. The outcome of your measurement should fulfill this table. And this seems completely impossible. People cannot prepare this, but spins somehow know what to do. We know that they cannot know it in advance because there cannot be definite numbers for these outcomes of measurement. They cannot fulfill this equation. The product on the left side is square, on the right side is -1. But rules of quantum mechanics, not very difficult one, tell us that this is what will happen in an experiment. And in fact, this experiment have been done. So the miracle that we can win this kind of game, which sounds impossible. Teleportation. Now, the Star Trek teleportation, forget about it. Because I don't know how much physics you study, but it cannot happen that the mass from here disappear and immediately appear some other place. There is a conservation of center of mass. Mass cannot jump. So the Star Trek teleportation is clearly impossible. How quantum mechanics may allow teleportation? Quantum mechanics tell us that all particles are really the same, identical. The electrons in my body and electrons in this table, or electrons in the rock on the moon, are exactly the same electrons. Protons are the same, neutrons are the same, all exactly the same. There are really laws. This is part of the laws of quantum mechanics, identity of elementary particles. You have tennis balls, they look the same, but they're not necessarily the same because they might be slightly different. Elementary particles cannot be different. They are exactly the same. So what makes a difference between me and the table? just configuration of these electrons and protons. In quantum mechanics, it's a quantum state of my elementary particles. So there is no need to move my electrons to the moon. All what I have to move is my shape. Me is my shape, is my wave function. Wave function is me, not really the electrons themselves. They're just degrees of freedom. There is nothing special about them. Nothing. So what since I'm the wave function, all what is needed is just to move the wave function. And you see there were kind of all kind of strange things. And let me repeat it. Let's say I'm here, and there is the same amount of elementary particles on the moon. So there is no contradiction with physical laws that I will disappear here. There will be kind of all particles are still here, but not in my shape. And maybe you heard about no cloning theorem. I cannot really create copy of me, but there is no contradiction that I destroy myself here and I will appear there. Now, it wasn't, as I said, today, it's maybe the most important protocol in quantum information was found like 30 years ago. And it's really simple. We start with these entangled particles, the EPRs, the most important, the most cited paper of Einstein. In fact, this kind of foundational paper, Einstein, Podolsky, Rosen, where they introduce these particles which have connection, which is stronger than classical. So you start with particles which are connected. These particles still don't have information about anything else. So here there is Alice. She wants to move a spin from which she will get, and she doesn't know the spin, to Bob, who is here. What she does, she takes one of this pair of EPR pair, which was prepared in advance, and performs, this entangled pair, they're really connected to each other in some strange way, but this is particular singlet state. So she takes the particle which she gets, make a measurement, combined measurement of this particle and this particle, which is called Bell measurement. And this Bell measurement on two particles, in fact, cannot have many outcomes, only four possible outcomes. Four possible outcomes is 2 bits. She sends these 2 bits to Bob. Teleportation cannot be immediate. Right? So locality is important. I cannot immediately move from here to there. I have to. I cannot break the speed of light. But still, there are some strange things. What Alice does, she sends only 2 bits of information. Bob makes some manipulation of his particle, and he gets the spin. What is a spin? Spin characterized by direction in space. Direction in space is a lot of information. Log sphere, we understand, to fix even on a plane, you have to put exact angle. 2 bits can say, let's say, up, down, left, right. So it will be kind of this area. But the spin gives exact position. There is exact position. If you'll put your Stern-Gerlach, it will tell you up. You change it, it might not give you up. Only there is one exact position. So what teleportation does, we have this preparation with these entangled particles, and then make this local measurement, send very little information, and send a lot of information. We'll set our direction to other place. Now I remember reading this CPR paper, teleportation paper. I was very upset. I read the abstract. I knew how to do it. I wasn't clever enough to ask the question. But at least it helped something, because I could immediately generalize it to continuous variables. Because with qubits, bits, you cannot send people. You will never send people because it's too complicated, but you can send electrons, wave function, states of particles, not necessarily discrete state. Now, the method is very simple, not very simple, very similar at least to the original teleportation paper, but instead of normal Bell measurement, the normal EPR state there, it was kind of EPR bomb state, discrete spin. Original EPR papers, they was talking about X and P. So replace spins and signaled by original Einstein-Podolsky-Rosen idea, and yeah, you can send me to a moon. The big thing, you don't have to send. If you send every molecule of me there, I will move there. This goes together. Don't, and one by one. Still, not feasible. Too many particles. Now, even here, I think it's a paradox. I believe that I'm something more than 10 to these numbers, because now it's not 2 bits. For every particle to move, you have to give 2 numbers. But still, I think there is more in me. But let's not talk about, anyways, this is science fiction to make teleportation of people, although sometimes you see on cover of some magazines. The paradox is in the original teleportation paper. Yes. No, there is a no cloning theorem, and which does not allow to make copy of me. And this Bell measurement completely destroy information about me. I'm not here anymore. And this particle is not here. But fortunately, after this manipulation given on this information, here it will be this state or it will be me. Okay, so the main paradox of teleportation, which I see here, is that we send information about 2 angles, essentially direction, which is infinite number of bits, by sending just 2 bits, the number from 0 to 3. Okay, so when I come to the many words, I want to explain what many word is. I think this is kind of a nice picture. We started with kind of 1 word someplace, 1 word where some stars in 1 position started, and then some quantum measurements were performed. Every division is really a quantum measurement. Every division splits the word to more words. And now, this is a small picture, but really there are many, many words. Now, some people say every second, every millisecond word split. I'm not sure. I really think no. Because I really can predict more roughly what will happen later. And the word is story. So I don't think there are too many splitting, because when there is splitting, I cannot really predict this result or this result. Every quantum measurement splits the word. Because what many words says that when we perform a quantum measurement, which standard quantum mechanics tells us that maybe up, some probability for up and some for down, many words will say, no, there will be up and down. If you will look on it, you will split. One of you will see up, another of you will see down. This makes physics nice. Without this, you have to believe in the collapse of the wave function, which is random and action at a distance, which I cannot believe. So it was invented by Hugh Price. He was a student of Wheeler. Wheeler accepted first, but then he sent Hugh Price to one of the fathers of quantum mechanics, Bohr, Niels Bohr. Everett came to Bohr, and Bohr completely didn't accept it, and Wheeler was kind of chicken out and didn't support Hugh Everett from then. I think he quit physics, and for a long time this was kind of very fringe interpretation. I think my paper like 30 years ago about many words, from then I'm working very hard, and not just me, but today in some papers you say that maybe it's the most popular interpretation of quantum mechanics. So what it is? First, there is only one physical universe. There is this big wave function which is entangled. We said these entangled particles are used for teleportation, for other things. There is a lot of entanglement, but there is a one-way function. There are multiple words. What's words? Stories, like what we know as words. There are many like this. Every time we perform quantum measurement, all outcomes happen, so they multiply. This is a kind of quantum way to write it. Psi is a one-way function. You write it as a superposition. Parallel words are in a superposition. So the word is experience of a single story. The word, what we any layman understand as a word. And the universe can be viewed in two ways. One way is just kind of very complicated entangled wave function. Another way, it's really superposition of these words. Now, words are really non-local because with this spin, you remember, they kind of have correlation. If I find up, he might find out. And the opposite. The words are all over. Every word is in every place. And the parallel word in the same place. But it's kind of non-local creation. So when we perform quantum measurement, what physics will tell us, it's not that one outcome will happen. We go to laboratory, we see one outcome. But physics will tell us that there is no explanation for one outcome. So all outcomes happen in parallel. And every time what is really happening, kind of more words are created. Inside the word, there is illusion of randomness. It looks for us the random outcome, up or down. And when this EPR Bell measurement happens, there is kind of non-locality. We measure something here, something there. In our world, changes. But if we'll take all words together, we do a measurement here, nothing changed there. The mixture of outcomes, before there was something, the mixture of these outcomes will not change what's there. In every word, there is a change. But take the mixture of them, and you'll get the original situation. Let's make an experiment now. This is my homepage. You are welcome. It's easy to find it using my name, my homepage. And then you can go and and there is a word splitter. So let's, and this is really connects to a laboratory. Here there are instructions. I'll tell you. You can split the word 2, 5, 3, 4, whatever. Let's split the word into 2. So you click here, and there are choices. So let's say I'll put here left, and then I'll put here right. Nothing happened here. This is just interface. But when I now hit on split, there will be quantum experiment. It will decide. It's not decided. Both will happen. What if I will be, if somebody, some student now is present in the laboratory, he will kind of see if it's left or right. So let's make split. No, something happened. Sorry. Let's try again. I hit probably the wrong. Sorry. You know, maybe it's not good. I made more splitting that I wanted. Left and spelled incorrectly. Never mind. Let me carefully click here. What's happened? I went again, and then it moved to another one. So there was no splitting until I put here no splitting. So now it will be splitting. Supposed to be. Yes. Right. So the idea is that since I get right, from this moment, I will move 2 meters to the right. And if I would get left, I will move maybe 1 meter to the left because there is no more place. But I know that there is another left there in parallel world. And now you look at me here. In this parallel world, you look at me there. This is what many world is. You perform quantum experiment. Again, if I don't have a good kind of, if I'm, never mind left, right, I will look to the right, maybe I will not split. But again, it will be different word because in one thing I think I fulfilled my promise and another one I didn't. So I will behave slightly different. So this is so we split the word, and you are welcome. It's free. In fact, 20 years ago I wanted to make a patent, but when I went to television university, they said to make some small device for splitting. Today there is an application for iPhone. For $2 you can do it, but you can go for free to my to my homepage and split the word whenever you want. So, okay. This is a picture of the first version. Now it looks different of this word splitter in Tel Aviv. And as a rough idea, it's not there is a single photon detector. This is the main thing there. And the rough idea is this: you perform an experiment. You see that sometimes this happens, the detector click, and sometimes the detector doesn't click. So you think this is a splitting of the two words in one. This will correspond to left or right, like here. What I believe that really we get both, left and right. Now, maybe a little about kind of what many word is. So if I split the word in two, some people say Schrödinger cat, this is kind of splitting. But there is a radioactive device which kills the cat, and it can kill the cat at different times. So there is a one word with a live cat and many words with dead cat at different times. Here you split just in two because there are only two detectors. And the particle, both click happened. Now, if I decide to move toward the detector which click, so I will go to two places. So from now on, the future will be slightly different. Know that some people say multiverse, different, constant. No, all physics is the same in every word. Outcome of experiment is different, so the word is different. Now, we can make the following experiment. You remember Mach-Zehnder interferometer? This is very much like this, but without second beam splitter. We send the particle, and now we know the two parts of the particle cross each other. Usually, the particles, if there are two neutrons, they kind of scatter. If there are two lefts, if I'll go here and another left here, probably I will not be able to pass. But this superposition, the equation tells us no problem. When we have this one level in superposition, I'm pretty sure there is a parallel left which walking here and maybe walking through me, no scattering whatsoever, no interaction. And we can do it in laboratory. We can test. The statistics of particles doesn't matter if we close one or not. No scattering. Maybe one more thing about many words. Some people say, oh, it's interpretation. You can say one thing, another thing. There is no technology today and in any near future to test the many words. But conceptually, many words are testable. It's not that it's something just story. How you test many words. Again, we are used to this source and beam splitter and two detectors, so we send. This is simple. This can be done. What is difficult to do is the following. Now, to test the many words, what we have to do, we have to undo the experiment. Our devices should be not so big, so we can keep them carefully and make them remember that they accepted, that they detected something. And if they detected, they should hit the particle back. So we have to do this kind of operation. If many word is true, then we send particle one from here and one from here, given the technology of undoing the experiment, which is very difficult technology. If many word is true, there is one way from here and one way from here, and they will always make constructive interference here and destructive here. This should be silent all the time. We repeat it many times, we see that this doesn't click, we know many words is true. Again, we need very difficult technology to do this, but in principle, it's not just philosophy story. This is kind of a real difference. If there is a collapse and there is only one, it comes from here, it can have 50% chance to come here. So we'll see the difference. Okay, let's come to resolution of our paradoxes. How this many word picture help us to see physics find that what was paradoxical before, how we can live with it, how we can understand it. So we have these three people, and they have these three spins, and they perform this measurement. And we know that there is no way, because of this, to fulfill this equation because of this property. So there is no way that nature know what, which measurement, which outcome to do. They measure sigma x, sigma x, sigma x. No way that they will know what to do. But there will be no contradiction in on every measurement you come and you know with certainty that you'll get both sigma x1 and sigma x minus 1. Sigma x b 1 and sigma b minus 1. What you need still unusual and strange, but maybe less strange, it's not action at a distance, connection between words. In every word, they will kind of correlate themselves. Words are non-local. When it's come, there are this plus, and will go with minus 1. And minus will go again with minus 1, but minus plus will go with 1. These are the words. There will be many words. Every outcome will happen. So we'll have 2 times 2 times 2 work, even just sigma x is measured. We have 8 words, but they will correspond rightly. So there will be no contradiction. Teleportation. What really happened is the following. We perform the Bell measurement. When we perform the Bell measurement, for every outcome of Bell measurement of this entangled particle, this one will be in different state. One result, it will be exactly the state which happened here, because this Bell measurement somehow knows the state which come. You make some measurement, and one of the results will be the original state which has to be teleported. There will be 4 different results. In 3 other results, this state will be rotated in a known way. But even before the rotation, before we have this entangled state, now we have a mixture of all these 4 results. And quantum mechanics tell us that there is no physical difference. In every word, of course, there is a difference. We had one mixture, this like entangled state, and it became particular state. This is action at a distance. In a single word, you started from here, you ended with one of them, which are clearly not this. You look on all of them together, they're equivalent to this. So nothing really happens when you perform a Bell measurement. No paradox, no action at a distance. Now, what happens? These 2 bits tell us which are the 4 words. Again, there are 4 possible outcomes, and these 2 bits will tell us what is the outcome. So this small information is not moving the direction. It just moves. Bob, Alice tells Bob in which word she lives, and when she knows in which word she lives, Bob make if one of the words he has to do nothing, another rotation of spin around z, x, or pi, 180 degrees. We end up in all of the words in the original spin. So there is no paradox. We got teleportation, and the whole information it's about the word. There is still the kind of strange thing. Non-locally, the words are non-local, and locally I can split them in the right way. So in every word, the information about the spin Alice got come here. And but my basic thing, there is no randomness. I know with certainty what happens. All of them come with certainty. And no action at a distance, because in the moment Alice performed Bell measurement, nothing changed on Bob's side. Bob gets this information, and then he rotates and brings to the state. Within physical universe, there is no miracle. The last one is this Elitsur bomb tester. You remember, you can get that this will happen. The explosion might happen. The miracle does not happen in this world. The miracle happens in the world when we get this click. When we get this click, we know that the bomb is here and this bomb is still fine. But in parallel world, the photon was there. It's the miracle to get information about some place without being there. This is against physics. But physics talks about all worlds together. Doesn't talk about just our world. In our world, since some strange things, we succeed to do this interesting phenomena. We succeed to know that the bomb, something which you're not supposed to touch, when you touch it explodes, is here without touching it. The price is explosion in the parallel world. I'm sure everyone heard about quantum computer. Very similar idea. In quantum computer, you put a particle, you split it to many, and you make many parallel computations. Now, there is no way to know outcomes of all of them, but there is a clever way to put some information from all these worlds and then to get useful information in our world. This is how we can get a quantum speed up in quantum computation. Okay, so our intuition comes from physics, and physics describe all worlds together. In all worlds together, physics is okay. It's deterministic, and it has no action at a distance. So these are conclusions. The Vaidman bomb tester provides information about presence of the bomb in a particular location without any particle being there. But in all worlds together, some particle was there. So the paradox is resolved. Bell theorem, GHZ, the nature is apparently random and it has some kind of action at a distance. No, if you look on all worlds together, it looks only within a particular world. Teleportation transfers huge amount of unreadable information using a few bits. All the information, it's about one of the four words. We split the word to few words, and this is the information we split, and this is enough. There is kind of miracle of, because the word is non-local, we do something here and we split it in a non-local way. So the many words removes randomness and action at a distance from physics. It explains why we have such an illusion in our world. Thank you, and you are welcome to ask questions. Yes. I think my latest paper on many words tells that you have to postulate the border. There are many, I don't know how much you read about this. There are many, Everett himself said that it's kind of come out of formalism. Then Deutsch, who is kind of father of quantum computation, said that you can get it out of formalism. And his student Wallace continued this very much, and others. And I think it's made a bad service to many words. I don't believe you can derive the Born rule from formalism. You have to assume something. Every other interpretation assumes something. Now, you don't have to assume much, and I have some proofs, and others, Deutsch, Wallace, and Zurich, and others. Everyone assumes something. What I assume, for example, is the same. I don't believe in action at a distance. So starting with symmetry and axioms that even within the world, you cannot send signals faster than light, you can derive the Born rule. You can read my paper on derivation of the Born rule. It's there.
Historical question. I'm thinking about times when the father of many worlds, John Wheeler, would visit us. And I'm wondering if you ever had, like when I would ask him, why did you put your name on this? He would have his typical famous Wheeler pithy statement. He said too philosophical, meaning he didn't believe that the things you've been arguing. My question now is, the last time I remember him coming to see us was like in '92. And all this stuff you were doing was just coming out then. I'm wondering if you ever had a chance to present him with any of this stuff.
I had the privilege to spend 2 hours with John Wheeler. But in fact, what we discussed is weak measurements. And we never discuss this. Now, there is this book, historical book on Everett and Wheeler and all kind of discussion. And what I mentioned in the beginning, I understand, I don't know too much history, but really is that Wheeler was very supportive until Bohr told me don't. So he kind Bohr said that he didn't want to listen. Bohr, he has, I think, again, I believe that there is a sociological thing, but the quantum mechanics was born. And then for 10 years, there was no Schrödinger equation. So it was kind of a miracle. And then Schrödinger equation and Heisenberg came together. So Bohr preached, and people start to believe that no one can understand quantum mechanics. This is how it is. Don't ask. There are events and probabilities. It's just recipe. But again, I'm not a good historian. This is what I understand. But
I remember that. I think he was moved a little bit towards the basement. I'm curious to see what you think about this.
yes.
So I think you said the only time you're sure when branching happens is following a quantum measurement. I just wanted to ask about that. So if we take the Tel Aviv quantum world splitter, what's happening there, what's creating the branching of worlds is that we're correlating a choice to move in a certain direction, left or right, with the state of a particle. The state of the particle's here, move left, it's there, move right. It's the superposition of here and there. So you branch. So if it's that easy for branching to happen, then why are we not branching the world right now? So for example, just what I choose to do right now, what I think is correlated to or corresponds to a neural network, a particular state of my brain. That corresponds to the states of the individual neurons. The states of the individual neurons, whether they fire or not, correspond to whether or not tiny particles, enough of them have entered into a neuron to cause it to fire. Those tiny little particles, whether they enter or not, I mean, aren't they in certain positions of multiple places? So whether I'm in a certain brain state, it's going to depend on these particles.
The crucial part of this Tel Aviv world splitter is a single photon detector. Single photon detector takes something microscopic and make it macroscopic. So when you have this transition, big amplification, then macroscopic, this is what the word is something when everything is well localized and well, there is one outcome. Now, I know I heard that if you're in the dark and you look, maybe 3 photons are enough for you to, with your eye. So this is also kind of a single photon detector. But now there are myriads of photons. So there are different stories. So in the special situation, many cases might happen, but there should be special situation. Nicolas Jezin was telling that if you take today's smartphone, its camera is so sensitive, so for the very low light, it's a world splitter. By Tel Aviv, just use your light, but again, it doesn't. I don't think it has interface for amplification. They really made an experiment. They took apart a smartphone and took the camera and made this amplification of this camera. And there are some people say that you take a coin from your pocket, and when you do it, because of some quantum part in your hand, it's also world splitting. Maybe. I don't know enough neurology. But I don't think there are too many. It will not be disaster for many words if there are many words, too many splittings. But I think it will be less nice because there are splitting all the time. We want to believe that kind of the normal story, the normal life, it's kind of deterministic life. And non-deterministic results will happen only in quantum type experiments. Yes. Why is what? I'm not sure what is related. Maybe you talk about Heisenberg uncertainty, so it's now here and then later not here, or
bombs in the same location every second. Why isn't the bomb in another location? Why is the bomb always there for your experiment?
no, but this is the experiment what is supposed to test. And again, for example, if you have two boxes and somebody tell you that the bomb in one of the boxes, then it's very easy classically to find the bomb without exploding it. Open one, it's not there. Okay, I know it's there. The advantage of this experiment that somebody tell you it might be there, you don't know, maybe there is nothing. If you get this forbidden click, you know that something disturbed you. So what you do, you kind of test first that every other place is free. This place you don't test, because if you test, if the bomb is there, it will explode. And then you run the single photon. If you get this click, you know that the bomb is there without exploding it. It's not that this is your task. If it would maybe not a bomb. If somebody just put some other obstacle, it also will be so. But what's important that if you test everything here and everything is free, and you got this click, you know that there is something there, and you can claim that in your world, no particle tested. I want to know if there is something under the table. I test my hand, I look at it. Now, somehow, without looking, without it, I know. The experimental paper about interaction measurement was seeing in the dark. So how you can see when no light is. Okay.
Okay, where's technical? We got you here. Just following up on Kelvin's question. So suppose we can see 3 photons, the eyeball. Supposedly, as far as I can tell, I mean, the thing called me that makes observation never experiences a superposition. Right? I always experience one definite. But the question is, if the eyeball, if the retina can do a quantum measurement at 3 photons, then is it possible you could get to? I remember you wrote a famous paper with Dave, right? It was on the year ago.
Yeah.
But the question is it possible you could get into a crazy thought experiment where by the time you have an experience, like a gestalt, you're in a little bit of a mixed up state. You're witnessing the transition or the you see what I'm trying to say? You have something that's more of a direct manifestation of two worlds. On thought or what it's not completely crazy. It's a potential, literally a thought experiment.
It's, the issue, what is experience when you have an experience? The many words tells you the following. First, the physics and the ontology is a quantum state, period. There are some other interpretations, put other things, so saying that you cannot talk about ontology. Then there is another very, very important part to connect this quantum state with your experience. And this you have to bring help of biologists, neurologists, psychologists, and whatever. In some simple cases, like here, there is the detector, and I see if it's click or not, easy. Boundary cases, we have to decide, but it's also vague. The word, the many word interpretation, but the word is our concept which help us to explain our experience. It's not ontology. The only ontology is just the quantum state.
Have any questions from the Zoom audience?
This is, yeah. Huh? No? Okay. Okay.
That's in the other world.
Yeah, we cannot see questions in another word. Maybe I mentioned that David Deutsch, who is kind of a big fan of it, succeeded to publish a paper in Physical Review, the journal for kind of particle physics, about kind of also astrocosmology and possibility of many worlds. And you can see yourself in some multiverse, but this is all related together with cosmology, which is, I don't think it's relevant to the story. And this is, for me, it's more like physics, science fiction. But in my many worlds, you cannot see what's happening in another world. The only interaction with other worlds that if you have super technology, you can try to interact them. Like if you perform the measurement and you're trying to undo this. Then, in fact, you split the world in two, and then you put these two worlds into one. And it's important that you can do it. And after Everett, it was DeWitt who publicized it wrongly. He was kind of saying that the worlds split and never unite. And then this theory is not attractive. The attractive theory is that everything is very simple, unitary quantum evolution. And the fact that we see one outcome and not many is because we built like this, and we have to understand evolution of why we are local. And this, I think, pretty clear follows from the locality of interaction in nature. Last question, maybe? Yeah? Yes.
Yeah, I'm just tempted to ask. So, when there's is there any associated thermodynamic quantity, like the example entropy of the universe that changes?
Yeah, but for me, quantum mechanics, the universal wave function evolves according to Schrödinger equation, and entropy is zero all the time. Now, it doesn't mean that I will say don't study thermodynamics and don't study entropy. It's very useful. It's for us. It's a practical. It's practical tool, and when we consider different situations, then it's useful. But conceptually, entropy doesn't play a role in my story.
Could say that entropy defines each individual world. Yeah. As you go forward and split further and further, your experience of entropy progresses in time in that way.
But also there is one of the essentially quantum mechanics allows you to talk in a rigorous way about entropy when you have a composite system which is entangled. You look on one of them and you can define entropy in a rigorous way. Because in any other way, it's just your ignorance, which is also useful. But here it's beyond ignorance. In your world, if there is some molecules entangled with some other ones, you can say, oh, there is an entropy for these molecules. And this is kind of a real fundamental ontological meaning inside the world. And the ontology is, there are many interesting things. There is this, the first approximation to find the physics for the universe. Then there are interesting phenomena inside world, like all these Bell inequalities, other things, and special experiment with post-selection, which with Aronov we work a lot. In a particular world in which this post-selection, there are some very nice features. These nice features are not universally for universe. It's just for my world in which I got this post-selection. And then I got some interesting things.
One more question. I just want to see, it's always wonderful to listen to the debates between Yakir and Lev. We always learn new things. He's famous for the debates. So I'm going to ask the Yakir question. I'm going to see where you're coming. How do you deal with Yakir's morality? Why should I just go round the
I spoke with Yakir for many, many hours about many words. And I still, in this world, yes. And I think he's the strongest, or at least the argument I know, that he's upset that if there are many worlds, then there is some probabilities that in parallel worlds, it was a traffic incident and he killed the old lady. And this is the reason why he doesn't like it. It doesn't convince me. I think doesn't convince me. I think, in fact, the fact that there are parallel worlds, if everything is good, then you don't think about it. If things are bad, then it's you can think comfortable. There are parallel worlds in which maybe life is better. So I don't. I think the many worlds is helpful for this kind of situation.
How come you're not robbing banks? Or are you robbing banks?
What?
What? Oh, you would tell me. You'd have to tell me if you were robbing banks. Why don't you rob banks? You know, his argument,
Yeah. Okay.
one version of Yakir's argument, he says that, well, if you live in many worlds, then I should rob banks because I know at least in some worlds I'll be rich, other worlds I'll be dead, other worlds I'll be in prison, but as long as in a few worlds that I'm rich, why doesn't everybody in the world just do that?
But in
What?
response to my question, you deny this though.
What?
If you rob a bank, there isn't some other world, or at least you don't know that there is some. Because you said the only time that branching is after a quantum measurement, but robbing a bank. is not.
Correct. He cannot be. No, he cannot be sure. But clearly, if there are parallel worlds, there are more worlds, and we don't know too much about them. When I perform quantum measurements, so I know then there is another lab which works differently, and maybe we'll end up lecture 5 minutes later or earlier, but it's not very different. Now, so there are different worlds. If there are different worlds, then there is a chance that he can delete this there. It's not that it's necessarily. Some people say many worlds, all worlds, everything happens. No, this is he doesn't have this strong. If there will be this strong properties, then I maybe accept this ethical argument. There is no, you don't know. And maybe there are some other worlds in which you was so ethical and save the world and whatever. But I don't know.
But okay, quantum money. We use quantum money, for example, and then it could be an issue.
I think
Yeah, like-
a simpler example is just that you use Lev's splitter to decide exactly which lottery number you're going to buy. And then in other worlds, every lottery ticket came up and you purchased all of them in one world. And one of you wins the lottery, guaranteed.
And the other ones you post.
The other ones you're down a buck.
You do a suicide post-election.
It was the only time I have been in this TV kind of things with answering questions, and I use this method. I was at least in this world. I didn't went far away, but I know that at least in one word, I definitely hit the million.
Remember Scott Aronson's proof of how to solve all NP-hard problems?
What?
Same approach.
Same approach?
Guess a random solution. If you're right, you don't kill yourself.
This is, I know, some philosophers not particularly like, but I have this concept of measure of existence, which answers this, because some people say, why not to use Russian roulette on a large amount of money? And I say, I care about the future worlds, although I know everything will happen. But I care about all my descendants in proportion to the measure of existence. And so then it makes my behavior more or less normal, although I might see some difference if I'm believer or not believer. But they are very subtle differences.
Some people really went forward with that, David. I know where it is these days. Some people followed up on this.
I don't know. I'm trying very hard to persuade David to bring him back to many words, and without much success lately. Maybe.
Spectacular. Thank you, Lev. That was a fantastic talk, as all your talks are. Thank you so much.